So welcome to this pre-recording of a lecture on symbolic computation. In particular, the topic of today is symbols, names, and references. So we will start with a symbolic computation, in which it is important that we can declare symbols. When we work with symbolic expressions, we compute essentially in a symbolic ring. Often we want simplification, but there are also situations where we want to prevent the simplification. And in the second part of the slide presentation, I will explain the mechanism to share values between variables. And we will also see how to prevent the evaluation of symbols when we make the connections between variables. So this pre-recording consists of two parts. In the first part, I will try with 4 slides explain the main concepts of today. And this is regardless of the computer algebra system that we are using. In the second part, I will demonstrate how this is done with Sage. Okay, so let's dive in. So let's consider a symbolic computation. So we have 5 symbols here, the letters A, B, C, and D, and essentially also the square root of 2. The square root of 2, as we have seen in an earlier lecture, can be interpreted as an unevaluated function call. Okay, so what do we do? So assume that this is on paper. We apply the distributivity law and we simplify. We group and we simplify. You see that if we have the square root of 2 times the square root of 2, then this simplifies to 2. And we can regroup. So in a way, we will see that when we ask Sage to do this, that Sage will not automatically perform this calculation because it is not immediately clear how this is simpler. So the last expression looks simpler to us because with hindsight, we already know what algebraic numbers are. Now, I should emphasize that I deliberately picked this example because it follows the lecture on algebraic numbers. But technically speaking, or actually literally, this is not an algebraic numbers. So this is a purely symbolic computation, and this is an example of expression manipulation. So it is a symbolic computation because we compute with all the symbols as if there were numbers. So that's another way to explain what is symbolic computation. Symbolic computation is also expression manipulation, and this is our first example of normalization. When we think of this evaluation of the product of two symbolic expressions, we see this as a normalization in the context of explaining how to compute with algebraic numbers. So this is not an algebraic number, but the symbols represent an algebraic number. So there's not an algebraic number because the A, B, C, and D, they are not rational numbers. But you can see the laws, so the product law of the computation, of the computation with symbolic numbers. As an exercise, work out the division. Okay, so coming back to the last lecture, why, if we look at the square root of x square, so where x is a symbol, why does that not automatically simplify to x. Knowing what we know, or what we should know from the previous lecture, we can immediately answer this, but I will delay this now in this pre-recording till the demonstration. We started this course, the first symbolic computation that we did was the sign of pi. And that was a clear example of an application of a function, the sign function, to a symbol. And that simplifies to 0. Now, it may be that we don't want this simplification, that we just want the expression, the sign of pi. Similarly, what will simplify in the square root of 4 will simplify to 2. Now, if we want to prevent this, then we must actually see the numbers as symbols, and most functions, most elementary functions, often allow to hold off the evaluation. So it's another way of delaying the evaluation. So in the explanation of the difference between symbolic and numeric computation in the first week of classes, I was explaining that the evaluation to a floating point number in a symbolic computation is postponed. In numerical analysis, we always work with floating point numbers. With symbolic computation, we will do this only at the very end of a computation. So holding off the symbolic evaluation seems here a little bit artificial, but if you've done ever any programming, then what a program does is actually it stores the symbolic instructions that are then evaluated at some later part with specific values for the inputs. So what we can see here is that this holding off of the evaluation is a little bit similar to when we think of evaluation of computer programs. Okay, so in the second part, or actually in the last part, we will look into the names and the references. So if when we assign variables, then there are some side effects, especially when these variables do not have values yet. Here is an example. So we have two names, x and y. If we assign y to x, then we have that x refers to y. And both x and y are names of variables. After we assign 3 to y, then y refers to 3. But since x refers to y, then actually what is the value of x? Then actually when you evaluate x, when you assign another letter to another variable, you assign x, you will also assign to that other variable, you will assign the value of 3. So this picture is the situation as you would see it as a programmer, and in particular as a Python programmer. We have objects that are not composite, so the simplest objects are numbers. Names refer to objects as a result of an assignment. So what are the consequences of this arrangement? So when you evaluate y, you follow the arrow and you obtain 3. But actually if you evaluate x, and we will see how this is done in Sage, if you evaluate x to the fullest, so you actually follow the link not only from x to y, but also from y to 3, then that also gives 3. And that is actually what happens when you assign with x at the right hand side. The right hand side is evaluated to the fullest. Now, of course, in the first assignment here, y does not have a value yet. So that's why you have this effect that x refers to the name of y. So what you can also say is that both x and y, they share the same object. So you can access the object tree via y, but you can also do this via x. So this has the advantage that if you are starting to change uh, the value of y, then you actually also change the value of x. So this is a very powerful mechanism for programming. It allows to manipulate objects without making full copies. So this is also efficient in a way. Okay, let's now continue with a question. So what if you had started with the assignment of tree to y? So you have the following picture. Y, the name, refers to the object tree. And suppose that without changing anything now to the situation, you would want to assign y to x without evaluating y. So in a way, this is another application of preventing the evaluation. Okay, so these are the three topics that we will see. We will see the computation with symbols, like one does when one thinks about writing a computer program where you do computations with variables. We will see this also here, how we can do this in a computer algebra system, and we will see how we can prevent the evaluation of expressions. Okay, so that was the first part, the introduction of the concepts. So let me now switch to the Jupyter notebook. So I have a fully prepared Jupyter notebook. But let me, for the dynamics, let me start from scratch. So I will show how to build up this Jupyter notebook. And actually the best way to follow throughout this course is to experiment also with Sage. So I have an untitled notebook in a 9.3 Sage mod kernel on Windows. I will rename this into lecture 6, and this is what I use in the recording. So the notebook that I just showed will appear on the course website. So it's now a good habit to illustrate. So in this lecture we illustrate symbols, names, and references. So this is the topic. So this is the lecture 6 of MCS 320. There will be 3 sections. So the first section is an example of a symbolic computation. So let us compute. So let me, so we remember from the slide, let us evaluate, so let us compute the product of a plus b times the square root of 2 times c plus d times the square root of 2. Okay, so the square root of 2 is already there, so by default Sage will not evaluate this, so I don't have to declare a symbol for that, but I have to declare variables for A, B, C, and D. So this can be done in one instruction. So this declares the variable names A, B, C, and D to correspond to the letters A, B, C, D. So strictly speaking, I could use capital letters or it can use other names. So what is the argument of the var is the string representation of the variable names. So typically the string representations correspond to the names. When I say that I will call a variable a, then I will also show it as a. Okay, so if I now compute with those, so here is my first symbolic computation. I will write this up. So I have the symbolic expression, so everything is typed, so I can verify this. So the type of x is a symbolic expression. Note that we have worked in the previous lecture with polynomials. This is not a polynomial here, not a polynomial even in several variables. It is a general symbolic expression. So in order to work, and also these variables here, there are general variables, so they don't belong to any specific ring other than the symbolic ring. Okay, so I have my other part, so I will work with the y. So the y is the second term in the product. Okay. And now I have my expression, so the expression is a plus b times the square root of 2 times c, so it's actually now ex times y, so I will use e for my expression. And you see that, well, I should also have pointed out, logically, because we are thinking about algebraic numbers, we see this as a plus b to the square root of 2. But you see that Sage has kind of another idea on this. So Sage sees this as a more complicated term, b times the square root of 2, which is now rearranged, and plus a, the simpler term. Sage does not evaluate this, so to force the expansion we have to, so to force the expansion we have to apply the expand method. So let's do this. So I have my expanded expression. Actually, the natural, perhaps I will change this. I should have used z if I'm having x and y. And my expanded expression, I call it easy. It's actually not easier. Although you see that it did one simplification. So the square root of 2 multiplied with the square root of 2 is 2. So you see there's already one simplification that actually happens. Now comes the harder part. I have to isolate the square root of 2. So I have to find the factor, which is the coefficient in the square root of 2. So here you see the BC plus AD, and that will be the factor. So let's call it G, the square root of 2, or perhaps I will write it as F times the square root of 2, and I will show that as well. So you see, I want to have that the square root of 2 comes after that, but I can't really force it like this at this point. We will see more about the structure, the internal data structures of expressions later in this course. Okay, so I have already the second part in my answer. Now the first part I have to subtract this. So I have to expand. So let me expand G, call it now H. And let me subtract from easy the rest. So let me the h. So I have now the rest. So that is the part that does not involve the square root of 2. And then my final expression is the rest plus g. So this gives me the expanded form, expanded and grouped expression. And it's also a way to illustrate the product rule to multiply two algebraic numbers, two general algebraic numbers, where the square root of 2 is one of the roots that was added to our number field. Okay, that was the first part. We're almost halfway this lecture, very good. So let me now illustrate the symbolic ring. So let me explain the question that you might have been answered already now. Why does the square root of x squared not simplify? Automatically. So first, before I forget, I have to reset, and perhaps I can do this a little bit cleverer. I can reset the variable. So note that I was using x before. So now x is actually simply x. So I declared x. X is actually one of the predefined symbols. So you don't really need to declare it. But to be a little bit pedantic, I declare x to be a variable. And then I have the square root. So let me call this s. The square root of x to the power 2. And you see that remains x, the square root of x to the power 2. Why is that? Well, just in case we forgot the previous lecture on complex numbers. So the square root, so unless x, if x can be complex, so the square root function is double valued for x, a complex number. So that was something that we pointed at in the previous time, so in the previous lecture. So I can force it. So there are several ways to do this. I could make assumptions on x, assuming that it is a real number. I can say that do the canonical radicalization. Perhaps I will have this wrong. The canonical radical. Yes, I have to cheat here. So it is the canonicalize radical. And there I still have this wrong. Canonicalize the radical. So what this will do, and this is a long command. So there is the normalization of kind of a synonymous but more an authoritative word, is to make it canonical. So if you want to canonicalize, means that you take the positive value here, and that simplifies things. Okay, so what about the other questions? So what if we want to see the, so I'm now saying it, writing it down in LaTeX notation. So the square root of 4, if you type it in, it will automatically just simplify. What if you want to prevent this? Well, you have to do two things. You have to cast 4 into a symbolic ring, and you have to say hold equals true. So, and I will give this a name, the square root of 4. And you see that this indeed has done two things. It has left the 4 alone. We saw 4 as a symbol. And the hold also prevents the evaluation. Okay, so I can evaluate, I can remove the hold. What I can do is I can do the unhold method, and that will do the simplification. So that will do the simplification and evaluate the function. So just like the square root of 2 was not evaluated, I can prevent the evaluation of any square root. Now for the 4, the square root of 4, why now again does the 4 become 2, the square root of 4 become 2, and then the square root of 2 does not get evaluated? Well, the value, the numerical value of the square root of 2 depends on the precision. So that is one situation where you want first to define the symbolic, the precision for the evaluation. There could also be a number field that you are using, and in that number field, you want first to define what is 4. So you want to set the context. Coming back to our original sign of pi, so I can do the same with pi. I don't have to cast pi into a symbolic ring, so I can just say hold equals true, and I can then show the sign of pi. So this shows the symbolic expression. And if I do the unhold, I will see the result of the symbolic, of this symbolic computation. Okay, that was the second part that I wanted to illustrate, how to prevent the symbolic evaluation. Now, the last part, how can we obtain that these different names share the same value? So I will have to talk about names and references. Okay, so let me reset all the variables to begin with. So I have two variable names, x and y. And what I do is I assign to x equals y, so that's an assignment. So what happens after this assignment? Let me print this out. So y equals y and x equals x. You see that y equals y and x equals y. So what do we have after this assignment? Because, so let me document this, because x and y are variables, so they're not assigned, they're truly still variables. We have that x refers to y, and I can use using the LaTeX notation, I can express this with the long right. Okay, so what happens now if I assign to 3? Let me do the same statements again. So y equals y, and here we will see 3. But what will we see when we do this with x? You see that x still equals y. So we have now the following situation. We have x referring to y and y referring to 3. Okay, so how can I check this? Well, suppose that I would do z equals x. Then it doesn't fully evaluate. So actually now I have that z refers to x and x refers to y. I'm sorry. So it evaluates only one level. So we also have now that z refers to y. Okay, so how can I force the evaluation? Well, I can evaluate the string, and that fully evaluates to 3. So we follow the arrows, x goes to y, y goes to 3. So to evaluate x fully, we apply eval to the string representation of x. Okay, very good. So I have one last thing to show. What if we actually started with the assignment of y to 3? So here is the problem I ended the slide presentation with. So what if we started with the assignment of 3 to y? So we re-begin again. I do the reset. I have x and y, my two variables, and I start with y equals 3. So what is the question now? How can I obtain the same situation? So now, let me state what I want to do. How can we obtain the following relationship between x and y? And by the following, I mean that we do have that x has to refer to y, while y refers to the object 3. Okay, so when I do the assignment, like I did the assignment of z equals y, or z, when I assigned x to z earlier, so let me scroll back up. So what happens when I did this assignment here, so it evaluated x to y. So I don't want that to happen. How can I do this? Well, won't let you too much into suspense anymore. So we can prevent the evaluation by putting quotes around the variable. So if I do now what is x equals, and what is y equals. Then you see that I have that x refers to y and y refers to 3. So the word equals now is actually not good. So actually I should have used consistently replaced equals with refers to. So let me pedantically do this. So this is refers to, that's the proper terminology, and this refers to. And again, if I want to force the evaluation, I apply the string representation to x and I evaluate. So there I evaluate to the fullest. Okay, so one extra thing. So I still have time. I can still run to the full 40 minutes. What if I want the following? So I will now have z refers to x, and while x still refers to y, and y refers to 3. Well, I will prevent the evaluation. So here is, I can say that z refers to x. And what I want to illustrate is that if I do eval the string representation of z, I get y. So I can write the following: z refers to, and now I have to apply the indirection, it refers to z, which in turn refers to eval string of x. And I can continue this. So let me copy and paste. So I can continue this game. I can, because I want to see 3, I can do eval string representation z. And now let's see if I didn't make any typos. No, I didn't. So the last part is a little bit technical. So I apply the evaluation twice, and also the string representation twice. So you can think of, we can continue even if there's more, you can think of a recursive way to peel off all the references. So working with shared references is very powerful. Again, we are here only referring to an object, a simple object, a number 3, but one can manipulate more complicated objects indirectly without having to make copies. So we had the relationship z refers to x, x refers to y, and y refers to 3. And this can be computed in one single statement, print statement. Okay, I hope this was interesting. So thank you for watching this pre-recording.